Hello everyone, my name is Xinyi Li. Today I'm gonna to talk about the project in my system engineering class and my final report, analyzing air traffic control system. In this presentation, there will be the following parts: introduction, background, concept development stage analysis, engineering development stage analysis, post-development stage analysis, challenges and lessons I have learned through this case study. So now let's start from the introduction of system engineering and the project. A system can be seen as a set of interrelated components working together to reach a common goal. System engineering aims at the realization of successful complex systems by interdisciplinary approaches based on the consideration of whole system. It will focus on defining the needs of customers and defining the required functions in the development cycle, and then documenting and proceeding these requirements with design, synthesis, and system validation. Complex systems like transportation system, automobile system, and many other systems that performs different functions to convenient our life. This project aims at learning system engineering through analyzing air traffic control system through the system development process, which contains three phases: the concept development stage, engineering development stage, and the post-development stage. The next part is background. Air traffic control was first used in Croydon Airport in London at 1920. It is a service provided by airport to make direction for the aircraft in controlled airspace and give advices for the aircraft in non-controlled airspace. Air traffic control system is a typical system that requires system engineering. It is constituted by air traffic control tower and area control center. Air traffic control tower perform the primary controlling of the immediate airport environment by visual observation and controllers. It is assembled by several components, including radar system for traffic approaching and departing, ground control system to control the movement areas such as taxiways, inactive runways, and holding areas, and the air control system to ensure the prescribed runway separation could exit at any times. Meanwhile, the Area Control Center provides the clearance and instructions for aircraft in and out. It contains components like Air Traffic Control Center to give instructions to pilots, another radar system to ensure the airspace coverage and flight traffic mapping. So now, if we want to design an air traffic control system, we would start from the concept development stage. It is the initial step at the system development process. We should analyze and plan the needs of a new system, analyze the feasibility of its realization, and specify the architecture to best meet the requirements of users. First, we need to analyze the needs of customers. I have divided these needs into three parts. First is the marketing needs. After the widely use of airplane in transportation, air traffic control is necessary for ensuring an orderly and safety taking off and landing in airport, which not only save time but also improve the working efficiency by avoiding congestion in airport. Also, air traffic control can be used to avoid collision among large amount of aircrafts in the same airport, which can provide a safety environment. Second is the security needs. With the increasing terrorist attacks related to aviation activities in recent years, we need air traffic control to represent the role of security and defensive. So, if air traffic control system detects some abnormal aircraft activities in their airspace, they can contact government or military as soon as possible. Finally is the technical needs. The old air traffic control was done by using different colored flags to instruct the aircraft, Well, in 1950s, after the radar and radio system has been widely used, the modern air traffic control system should be upgraded with this new technique, so the controller can communicate with pilot by radio and the radar can provide a much wider coverage of airspace. The second phase in concept development stage is concept exploration. With the above needs analysis, air traffic control system can be defined as a system that provides organization for the traffic in their airspace, like control the order of landing and taking off, and control the space between aircrafts, and also perform the defensive when attack happens. This big system can be divided into two main subsystems. One is a visible control center, which can directly see the airport to provide primary instructions for the aircrafts taking off and land. Another is a local control center, which ensures the airspace coverage and can map the flight in their airspace. In order to achieve the function of visible control center system, some requirements should be considered. First, the center should be built in or close to the airport to have a complete view of the airport. Thus, a tall tower with large windows would be the best choice. Then, to provide instructions to aircraft, there should be controllers communicate with pilots through wireless radio, and the radio system should be good quality and less affected by interference. Apart from the controllers, there should also have approach and terminal control system, which is responsible for control the altitude of aircrafts after they taking off and ensure an appropriate landing rate when they are landing. Also, the control center should be configured with radar systems so it can provide aircraft location information to the controller. In addition, the control center tower should collect the data of aircraft in the ground before they take off and make sure the clearance of the flight route to avoid collisions between aircrafts. In local control center, it should be compiled with the radar system to map the flight in airspace, which can ensure the space is big enough between aircrafts to avoid potential congestion. Also, it could prevent aircrafts en route by mistake from other airspaces or interfering with flight route. Apart from that, local control centers should also deal with emergency requests like supporting pilots or contacting hospital. The last phase is the concept definition. After the concept exploration, the functions of subsystems and their components of air traffic control system have been clearly to meet the requirements of air traffic control system and in the consideration of operational cost and risk. Some concepts should be selected from concept exploration. As well known, the most basic and important function air traffic control system should be the ability to organize and control the air traffic flow in their airspace. The technique for building these two systems is mature and the cost is relatively low compared to developing new technology. Thus, wireless radio system for communication and a radar system for detection should be configured. The traffic control tower is also important as it provides the working environment. Building a tower costs a lot. Thus, the location of a tower, the height of the tower should be considered carefully. Approach and terminal control are necessary as they ensure the safe and successfully take off and land for aircrafts. As the ground aircraft control can provide an orderly control for aircrafts waiting for taking off in the airport and make sure there would be no collision between these aircrafts. The local control center should be selected as a subsystem for the air traffic control system. Also, the ability to deal emergencies is indispensable in the airport. The engineering development stage in system engineering can be divided into advanced development phase, engineering design phase, and integration and evaluation phase. Advanced development phase connects the concept definition phase in concept development stage and the engineering design phase, which would provide the basic for a full-scale engineering by validating the approach of system design through analysis and development. Engineering design phase mainly focuses on component engineering, component test, and some specialty engineering. Its output is an engineered prototype and test requirements for the system. Integration and evaluation phase is needed for the system that is not perfectly engineered and aims at building a more maturely system through different tests and operational evaluation. Advanced development aims at resolving uncertainties to provide a full-scale engineering environment. The method used in advanced development, including requirements analysis, functional analysis, and design prototype development and development testing. Different with the need analysis in concept development stage, requirement analysis method aims at analyzing the functional specifications of the system with consideration of not only their derivation from operational but also their performance requirements. Functional analysis and design is focused on the components and subcomponents that analyze the allocation of the functions and also identify the functional elements with similar functions in other systems. In prototype development, the physical implementation would be identified, including unproven technology, and in order to reduce the possible risks to certain acceptable levels, this method would determine the required level of analysis, development, and test. In some systems need to be mass production, like computers and automobiles, it's important to use prototype development method to design, develop, and build prototypes of critical components and subsystems. After test and evaluation, prototype development could correct the deficiencies feedback. The last one is the development testing method, which is used to test the system by creating test plans and criteria for evaluating critical elements in order to build a mature and validated system design. In air traffic control system, the primary idea is to ensure an orderly traffic flow for both pilots and passengers, meanwhile provide information and other supports for pilots. Thus, like mentioned in concept development stage, air traffic control requires a traffic tower subsystem to perform a visible observation of the whole airport to achieve the primary traffic control. For example, when the aircraft's taking off and landing, this tower should be tall enough and windowed structure located around the airport. Also, air traffic controllers are needed to realize the function of air traffic control system tower. They are responsible for separating and making efficient movement of aircrafts and vehicles in the runway, also responsible for the aircrafts near the airport, generally 9 to 18 kilometers. Air traffic control tower can be divided into several components, including local control or air control, ground control, and flight data or clearance delivery. Local control or air control is in charge of the active runway surfaces. It should clear aircrafts for taking off and landing in order to ensure the separation in runway prescribed could exit all the time. In local control, radar is used to show the map of the area, the position of near aircrafts, the identification, speed, and other information about aircrafts required by the local controllers. Ground control is responsible for the areas that aircrafts can move and also responsible for areas like taxiways, inactive runways, holding areas, and other areas that are not released to the aircrafts. The goal of ground control is to provide a smooth operation environment as it impacts the sequencing of departure aircraft. Also important for maintaining the safety and the efficiency of the airport. Flight data and clearance delivery plays the role of providing the most current information to both air traffic controllers and aircrafts, such as weather condition, airports ground delays, runway closure, and others. These three subsystems all have a communication component to communicate among each other, which is normally done by the radio, but sometimes can also be done by aviation flight signals for those aircrafts or vehicles without radio. However, in some busy and big airports, some more advanced radar and radio technology should be used to keep the accurate and efficient traffic flow management. As a result, advanced radar and radio system prototype should be implemented and tested. Air traffic control not only responsible for the control between aircrafts and their source and destination airports, but also responsible to providing service between airports for aircrafts in flight. So, area control system is another important subsystem to constitute the whole air traffic control system. Area control should in charge of a large airspace and the airports within this airspace. When the aircrafts depart from an airport or terminal's airspace, the area control center should provide instruction until the aircrafts arrive at the destination airport or terminal's airspace. The main information the local area control center should provide to pilots are the following: the altitude they are assigned to reach after they depart from the airport, and the altitude restriction they should meet when near the destination airport. Meanwhile, the local area control center should also ensure the separation of aircraft in flight from other aircrafts within the airspace, and when the aircraft is arriving its destination, local area control should provide the traffic flow to many airports to prevent the congestion among all the arrivals. Area control system has a major component, which is a radar system. To ensure the large airspace, the radar system used in area control including en-route radars, air surveillance radar, precision approach radar, and surface movement radar. En-route radars provide initial detect and determine the speed, position of the target aircraft. Air surveillance radar is used to detect and display the position of an aircraft. It is an approach control radar and often located in the terminal area. The reason of using air surveillance radar in air traffic control system is that it could provide reliably detect and track of aircrafts at altitude below 2,500 feet and also within 40 to 60 nautical miles of their airport. Precision approach radar should be used to provide guide to pilots, making sure the aircrafts can be landed in bad weather conditions. Surface movement radar can be used in adverse weather conditions. Its antennas are generally mounted in the control tower, so it has a better visibility of the area and also would have less influence compared to the ground surveillance. Another important component in area control is the traffic control over oceans, in which the radar system cannot be used as there is no radar system available over oceanic areas. As a result, the controllers in oceanic areas could use another air traffic control method, which is the procedural control. The information of the flight on the flight progress strips is recorded and also record the position report of aircraft in computer systems developed for the oceanic air traffic control, and controllers use these position reports, time, altitude, speed, and distance to ensure the separation between aircrafts. Engineering design phase would focus on component engineering, component test, and specialty engineering. Reliability, maintainability, and productability are three typical characteristics should be considered in a system. Reliability means the probability of a system would successfully complete its function. However, it is hard to observe failures in a complex system, like air traffic control system, as it has many interacting components. Thus, mean time between failures are used to present the reliability of each component in the system. Then the combination of mean time between failures by appropriate way can be seen as the reflection of the system's reliability. Maintainability measures the degree of difficulty of accomplishing the functions required to maintain a system in a fully operable condition, generally represented by the maintenance time. There are three important factors should be considered carefully when designing maintainability, including modular system architecture, replaceable units, and test points and functions. In order to achieve high maintainability, it is vital to have a high degree of system modularity and simple interfaced components that is self-contained. Thus, the engineers should consider the modularization design of the air traffic control system, such as communication modular, control modular. Replaceable units refers to the accessible, simple, and safety replaceable units when repair a failed part in place. It could affect the time for maintainability. As the maintainability time should be as short as possible, test points and functions are necessary to identify the location of a failure to a specific replaceable unit, and also when to converge on the failed unit. They could keep a short sequence of tests. For systems would be produced in large quantities, one of the major design objectives should be how to reduce production costs. Producibility can be seen as a measurement of the cost of production. The following factors could be considered to make the production easier. First, engineers could maximum the use of commercially available parts and subcomponents, and also maximum the use of stampings, castings that suitable for high-rate production. Additionally, the dimensional tolerance of mechanical parts can be set within the normal precision of production machinery. Engineers should find the trade-offs between the reliability, maintainability, and productibility to generate a test and evaluation plan and an engineered prototype for the integration and evaluation phase. Integration and evaluation phase is the last phase of engineering development stage, which aims at validating production designs and specifications. Integration is an important process because some unforeseen incompatibility would remain until all the elements in the system are brought together, even all the individual components have been tested well. As a result, engineers should consider the inputs and outputs of the system to evaluate the test results after the integration of system. The inputs include all the conditions affecting the system's operation, like the primary inputs of the system and the interactions with outer environment. The outputs that are required for accessing performance should be recorded and converted into measurable quantities. In air traffic control system, the input for testing contains the identified information of the aircraft, like the speed, position, and other information provided by radar system. Its output should contain the guidelines for pilots and taking like the taking off and landing time of the aircraft, the management of traffic flow in the ground airport. Finally, the test results could be analyzed through some system models, such as flowchart model, finite state motion model, state transition matrix model, and the nonlinear system dynamic models. So now let's talk about the post-development stage. Post-development stage is the last phase in system engineering lifecycle model, including the production, deployment, operation, and support for the system throughout its useful life. After the system successfully completing the operational test and evaluation, the post-development stage starts, which is released for production and subsequent operational use. Production is a vital factor in this stage, which is to realize the engineering designs and the specifications discussed in the engineering development stage to identical size of hardware and software components, and then aggregate it together into a validation system suitable for users. Thus, the affordability, reliability, safety, quality should be focused when transiting from development to production. Another major factor in post-development stage is operation and support. Through activities beyond the system development period are included, it still requires support from system engineering. Though activities beyond the system development period are included, it still requires support from system engineering. For example, when facing unanticipated problems, the post-development stage would require urgent resolution. Apart from that, with the increasing development in technology, the system often needs in-service upgrading. In air traffic control system, the post-development stage includes the investment of production tools and test equipment, construction of air traffic control tower and area control center, the operation of different radar systems, the training of controllers in airports, and other important components. Now I'd like to talk about the challenges met in design air traffic control system from traffic volume, weather, and knowledge. When an aircraft lands down, it will first touch down, slow, and then exit the runway before next aircraft land, which would need about 1 to 4 minutes. However, there are up to 5,000 airplanes per hour in the US. At rush time, even the large airport might cannot handle such large traffic. Thus, delay occurs every day. Adding more runways or building larger airport seems to be a good solution, while the cost and time needed would also be large. Thus, how to balance the increasing volume of traffic with the limited capacity of air traffic control system should be a considerable challenge in the future. Weather is another important factor that impacts the traffic capacity. Aircrafts need more time to land in bad weather conditions like rain, snow, and it also needs more space between aircrafts to avoid collision, which would cause the ground delay. Sometimes extreme weather conditions would even cause some serious safety problems when landing and taking off. As a result, how to minimize the loss due to bad weather could be a challenge to engineers. As mentioned above, air traffic control uses wireless radio and radar system to realize control function. Although these two technical systems have been maturely developed, there still exist some risks. For example, extreme bad weather could affect its stability, which would cause unstable connection between aircrafts, and the cost for maintaining is also high. Finally, I'd like to talk about the knowledge of system engineering I have learned from analyzing air traffic control system. First is the role of system engineers. From the air traffic control system analysis, I have a deeper understanding of what is system engineering and the role of system engineers when designing complex systems. Though the systems engineers don't require to design detailed components, they still need to understand the roles and the relationships between all components and systems. Especially system engineers should have to think of the whole, not only on single components. Then I knew the method used to development a new system. System life cycle is an important model in analyzing, designing, and producing a new complex system. In its early stage, the work mainly involves analysis in concept, then to engineering, development, and testing, and the final phase is to support and operation of production and use. Apart from the method in system engineering, I also learned several styles in system engineering, including robust, robustness, elegance, balance, growth capability, visibility, reasonableness, complexity. Robustness could be mainly contributed by margin and fault tolerance. A system with robustness would be more stable and thus would decrease the cost of operation. A balanced system means all the disciplines of the system are considered and working together well. However, sometimes it is difficult to achieve a real balance, as different elements have different weight in design. Even in balanced design, there still exist disciplines that are more important than others. Engineers have to locate more resource on those important areas. Growth capability represents the scalability and extensibility. Scalability is the ability of a system growing to handle larger amounts of its current function. Extensible is the ability of the system to be grown to provide additional functionality. To achieve the goal of growth capability, engineers can design and build the system on standards, especially on interfaces, monitor and manage margins during development, and set the growth targets. System engineers should also put attention on the visibility when designing the system, through providing instrumentation, alert and warnings, and access point in verification process to view system internal function. With the development of technology, evolution and revolution both in an explosive increase, thus it is necessary to apply reasonableness tests when attempting both evolutionary and revolutionary progress. The last key aspect of the styles of system engineering is complexity, which can be critical for engineers. To reduce the system's complexity, one of the best ways is to establish layers when defining a system that it minimizes the interaction between components. Failures cannot be avoided in system engineering process. System engineers should take failures as an option or as a chance to consider every step in the designing in order to avoid the same failure next time. It also provides a way to reassess. Through failure, engineers can think about how well the communication and the cooperation within the team. They can reflect the level of accuracy and the veracity of the assumptions made, and also they can view the perspective of the problems defined again to find out the way to resolve failures. In engineering economy, the most important concept is the time value of money. When designing new system, engineers are required to use evaluation tools for cost analysis. Money can also be represented by set of time effects on its value. Engineers should think about the interest and inflation in system engineering. In conclusion, development process in system engineering mainly refers to the revolution of a new system when its needs are required and technical approaches are identified. This report focuses on the system life cycle model in analyzing the air traffic control system from three stages, including concept development, engineering development, and post-development. Then, the challenges for engineers in this development process are listed and discussed. At last is the lessons I have learned about the method used in system engineering from this case study. So that's all the presentation. Thanks for watching.